This video is a continuation of the Chapter 4 multiple choice test corrections. Number 16, in which species does sulfur have the highest oxidation number? So you need to remember from your notes sheet how to assign oxidation numbers. Notice that things in their elemental form have an oxidation number of 0. So this would be 0. Hydrogen is always positive 1 with a nonmetal, and so sulfur would be minus 2 in that case. Sulfur here, since oxygen's negative 2, must be positive 4. In this one right here, hydrogen's positive 1, there's 2 of them. Sulfur's some oxidation number. Oxygen's negative 2, and there's 3 of those. Add those together and solve a little math problem. You figure out that sulfur must be positive 4 as well, because it all has to add up to 0. And then in this one, containing the sulfate ion, potassium's plus 1, there's 2 of those. Sulfur is some oxidation number. Oxygen's negative 2, and there's 4 of them, and it has to sum to 0. So that means sulfur must be positive 6 in this case. So E is in egg. Write down why you got it wrong. Write down what you will do so you don't get one like this wrong in the future. Number 17, which reactant is the Bronsted-Lowry base? So you need to know your definitions of acids and bases. You know that acids are proton donors. They're ones that give away H's. Bases are proton acceptors. They accept H pluses. So if you look from one side of the reaction to the other, they give you 2 choices. You can see HCO3 minus. The carbon-containing species over here becomes H2CO3. Therefore, it is a base because it gained a hydrogen from this side to this side. If you look at HNO2, it actually loses a hydrogen from this side, so it must be the acid. So the only one that can be a base in this case is HCO3, which is number 2, and that's letter C, as in cowboy. Right? Why you got it wrong and what you need to know in the future to make sure you don't want to get one wrong like that again. Number 18, another acid-base question, a Bronsted-Lowry base in the reactants portion of the reaction listed above. So that means on this left-hand side right here, what's acting as a base? Remember your definition of a base? A base is an H plus acceptor. So we want to make sure that it accepts a proton from this side to this side. You'll notice that the nitrogen-containing species has 3 hydrogens here. Over here it has 4. So it gains 1 hydrogen. So NH3 must be the Bronsted-Lowry base from this side to this side. And Na is another possibility with NH3, but you'll notice Na really doesn't change from one side to the other, so it can't be a base. So A is your answer. Write down why you got it wrong and what you'll do in the future so you don't get one wrong like that. Number 19, a precipitation reaction. The addition of sulfurous acid to barium hydroxide. Net ionic equation for the reaction is, so you need to be good at writing the reaction. Sulfurous acid, H2SO3 with barium hydroxide, BaOH2, a strong base. Swap the partners, you get barium together with the SO3. SO3's got a -2 charge, barium's +2. If you forgot the charges on those, barium's right here in group 2, so it's got a +2 charge. You could also look at some of the answers here and you could figure out what some of those things are. And then the other product will be water. Balancing the equation, you needed 2 here, and I believe that makes it so it's balanced. Now you have to go through and decide what things to split up and not. This is a weak acid, so leave it together. This is a strong base, so split it up. This is a barium sulfite is going to be insoluble, BaSO3. And you didn't memorize it as anything else because it doesn't contain sodium, potassium, nitrate, or ammonium. So you must assume that it's insoluble because it's not one of those containing things. And then water, of course, is molecular, and you have to leave that together. So really nothing cancels once you write it in the ionic equation. And the only thing that splits up is the barium and the hydroxide to make these guys, and the answer is B as in baboon. Write down why you got it wrong and what you'll know in the future so you don't get one wrong like that again. Moving to number 20 now, we move into the quantitative aspects of the test. There's a bunch of calculating without a calculator, moles, mass, molarity. And so the next 4 questions are based on this reaction. Talks about which is closest to the number of moles of ClO2 needed to react complete with 100 milliliters of 0.2 molar MnO4. The steps to these are fourfold. You already have these written down in your notes, where first you need a balanced chemical reaction, convert to moles, do the mole-to-mole ratio, and then convert to the asked for units. In this case, they give you the molarity and the volume. So using the molarity triangle, you can convert to moles. Moles are equal to 0.2 molar, moles per liter, times 0.1 liters, because that's what 100 milliliters is, which gives you 0.02 moles. And then this 0.02 moles, remember, is of MnO4 minus solution. And if you look, MnO4 minus is related to ClO2 by a 4:3 ratio. So moving to step 3 now, the mole-to-mole ratio from the balanced chemical equation, put a multiply sign, put a line, put MnO4 minus in a position where it's going to cancel, and put ClO2 as your new set of units, because that's the thing you're looking for. And there's a 3 and a 4. So my recommendation on one of these is to take this number. Well, you can probably try to do it in your head and find 3/4 of 0.02, or you can try it like this. 2 times 10 to the negative 2 times 3 divided by 4. And now just take the 2 and the 4 and divide them. So you need 1/2 of 3, which is 1.5, times 10 to the negative 2. 1, 2 back would give you 0.015, which is D. Write down why you got it wrong and what you know in the future, so you won't get one like this wrong again. Number 21, which is closest to the number of moles of hydroxide ion produced if 6 moles of ClO4 minus are formed. So using the steps now, using the steps that you have written down, first the balanced chemical equation, that's done for you. Second, convert to moles, it's done for you. So now you go to the mole-to-mole ratio. So it tells you that there are 6 moles of ClO4 minus. Okay, it tells you that right here. And it says what's the number of moles of hydroxide. So put ClO4 minus in a position where it's going to cancel. Put hydroxide as a new set of units. There's a 4 in front of the OH. ClO4 minus has a 3. And so 6 divided by 3 is 2, and 2 times 4 is 8. So 8 moles should form, which is in D as in dog. Please write down why you got it wrong and what you'll do in the future to make sure that you don't get it wrong again. Okay, on to the next one, which is closest to the moles of MnO4 minus in 100 milliliters of 0.1 molar solution. So actually this is just simply a molarity triangle question, because all they want you to do is convert to moles. Moles are equal to molarity, 1 molar, times the liters, 0.1 liters, and so 0.1 moles is the closest to that number of moles, which is letter C as in cat. Write down why you got it wrong and what you will need to do in the future to make sure you don't get one like this wrong, a molarity triangle question. Lastly, 100 milliliters of this and 100 milliliters of MnO4 minus are reacted with excess H2O. MnO4 minus is the limiter, which is closest to the number of moles of ClO2 remaining after the reaction is complete. So they tell you the limiter, so you have to work the problem based on that. Step number 1, write the balanced chemical equation. Step number 2, convert to moles. So you're going to have to take both amounts and convert them to moles, and then do a mole-to-mole ratio with the limiter. And then we'll have to do a little subtraction to find out what's left over. So we're told that MnO4 minus is the limiter, so 1 molar times 0.1 liters. Molarity times liters is equal to moles, so we have 0.1 moles of MnO4 minus. This is the limiter, so compare it to the one that we want to know what is in excess. So put MnO4 minus in a position where it's going to cancel. ClO2 minus is my new set of units. And looking up at the balanced chemical equation, ClO2 has a 3 in front of it. MnO4 has a 4 in front of it, so 4 to 3. So 3/4 of 0.1, I guess you could say, is 0.075 moles of ClO2 minus will be used. And now they tell you the amount of ClO2 minus that you have to start with, but they don't tell you the number of moles. So what I can do is once again use the molarity triangle to find the number of moles of ClO2 minus in there, taking the molarity, 1 molar, times the liters, 0.1. So I have 0.1 ClO2 minus to start with, and then subtract from that 0.075 moles. And so my leftover is 0.025 moles, which is letter C as in cat right here. 23 is C. Write down why you got it wrong and what you'll need to do in the future to make sure you don't get it wrong again. Last page, number 24. Which is closest to the molar concentration of Na plus in 0.5 molar Na3PO4? So if you know that it's 0.5 molar, you know that this entire species is 0.5 molar, but they're asking specifically about this guy right here. Notice how many sodiums are inside this. There's 3, so you need to multiply it by 3. 3 times 0.5 is 1.5 molar, which is C as in cat. Write down why you got it wrong and what you'll do in the future to make sure you don't get one like this wrong again. Number 25, approximately what mass in grams of this guy is required to prepare 1,000 milliliters of 2 molar magnesium sulfate? So first of all, this is a prepare a solution problem, and you'll need to find out how much of this you're going to need in moles. And then from there, you can convert to mass in grams using the molar mass that they give you. So moles are equal to the molarity, 2 molar, times the liters. This is 1,000 milliliters, so that's 1 liter. 2 times 1 is 2 moles. And then take this 2 moles, and in 1 mole, there are 192 grams. So 2 times 192. Well, it's not going to be 192, and it's definitely not up above 576, so it's probably going to be this 384 right here, which is B. Write down why you got it wrong and what you'll do in the future to make sure you don't get one wrong like that again. Next one, let's see, 0.5 liter solution of 0.5 molar ammonium tartrate is diluted to 0.1 molar. Which is closest to the amount of water added to the solution. So it tells you that it's diluted, so now you can think in terms of the M1V1 is equal to the M2V2 solution equation. The initial volume is 0.5 liters